Okay, so last time well, I've been doing a lot of slides, so I thought maybe it would be helpful to maybe just go over the general structure slowly so we at least understand what I'm kind of talking about here. And maybe I can highlight, um, well, just some things that are are kind of known, and then I'll go back to the slides. But I think it might be kind of helpful to see how all of these structures are sort of tied in together, right? So you sort of have graphic structure. Okay, so we have graphs. Okay. Now, we have talked about directed graphs too, which I guess we can add that to the list of sort of graphic structures. Okay. So directed graphs, you sort of have a direction as intrinsic to the property of the graph. So this is a digraph, right? Okay. We also have there's actually another type of sort of directed graph that's related to sign graphs, and that's actually called the bidirected graph. So every edge, each end of the edge, you actually give a direction to this thing. That's actually called a bidirected graph. Okay, so a bidirected graph. I'm just mentioning this because I'm about to show you a hypergraph generalization, and that's related to this structure as well. So I haven't really talked about that one, but every bidirected graph gives rise to actually a signed graph. So a signed graph, we talked about before, is just you're giving each edge is assigned either a +1 or a -1. So you can think of it as giving it a weight. There actually is something called a weighted graph as well. So this is a signed graph. Okay, and then last time I started talking about complex unit gain graphs. Okay, but so this one is a little bit stranger, but every edge has two orientations to it, but it's different from a directed graph because a directed graph, when I look at this edge, that direction is sort of intrinsic to the property of the graph. Whereas with a gain graph, there's no, if I just talk about this edge, each orientation is going to be given a label, but it doesn't mean that I have to say flow from one vertex to the other one. It just happens to be, if you go from one vertex to the other, you can talk about what is sort of the assignment of your weight there in a sense. Okay, so every edge has two directions, and what you're going to do is you're going to label each of these directions with a complex unit. So for example, if I do label this as a +1, then what goes in this direction has to be the inverse of +1. So if this is a multiplicative group, that would be the same as itself. But let's say that I labeled this direction as I, the inverse of that would be -I. If I multiply -I and I, I'll get negative times -1, which is +1. So that's how I know. If they're complex units, they're just going to be conjugates of each other. Okay, so let's just say the rest of these are like -1, -1, +1, +1. Okay, this graph is it's really complicated to write all of those directions. So what you can actually do is simplify it and just write one direction, because the other direction is just going to be the inverse. Okay, so if let's say that I write these directions. So this would be a +1, a -1, +1, and a -I. You see that simplifies the picture. I know what the label is in the other direction, but the difference between this and the digraph is just the direction in which I'm drawing that does not actually mean that that's a fundamental property of the graph. Okay, so this right here is what's called a complex unit gain graph, or a T gain graph, or a T voltage graph. Okay, and you can generalize this too. You can actually assign, you can do the same thing, but label, you can pick any group that you want. So, and you call that a G gain graph, where G is a group. Okay, and you actually do the exact same thing. Whatever I label in this direction, let's call it little g, what's going in the other direction has to be G inverse. Okay, so you can pick any group that you want, but the reason that this family is really nice is the matrices that you get from this family generalize the ones over here much better. If I arbitrarily choose a group, the matrix, I'm not going to be able to necessarily generalize all the stuff that I know from linear algebra. Okay, for example, if you look at the adjacency matrix for graphs, sine graphs, and complex unit gain graphs, they all have this symmetric property. Okay, but if I haphazardly choose a group here, let's say that I chose all complex numbers, not just the complex units. Now the inverse is not going to be the conjugate, and so the matrices there will not be symmetric. Okay, maybe I should give you a quick example of that. Would that be helpful? Okay, like down here, let's just do one edge. Okay, very simple, one edge. Okay, graph, one edge, that's say a sine graph, one edge that's a complex unit. Let's do I and minus I. And then let's do a general group. Let's say G and G inverse. Okay. So what would the adjacency matrix for each of these look like? Okay, well, this one, I have zeros on the diagonal, and then I'd have +1, right? Because these vertices are adjacent to each other. The sine graphs, well, it's still zeros on the diagonal, and now that adjacency is -1, so I'll have -1, -1. Over here, I'll have 0, and then let's say that this is V1 and this is V2. So from V1 to V2, I will label whatever the gain is in that direction. So I'll put an I here, and then the gain in this direction is -I. Okay. Now, if you stare at that matrix, you'll say, okay, well, that's not symmetric in our classic sense. If you take the transpose, do you see that the negative will go up here actually? But the complex symmetric is, so down here, you see that A is equal to A transpose, right? And for this one, it's still the same. This one, it's actually A equals A transpose conjugate. And that right there is sometimes labeled A star, okay? So this is, you'd say that this is symmetric, and this is symmetric. This is, the name for that is, you could say it's complex symmetric, but more commonly it's Hermitian. Okay, and most of the properties that we had about symmetric matrices carry over to the complex cases here. For example, remember the eigenvalues are real? That's still the case here. So for example, eigenvalues are real, and many other properties. Okay, same thing here. And here. Okay, but what about this? Well, just kind of following the same procedure, I'd have 0, G, minus G, or sorry, G inverse. It could be minus G if it was an additive group, but it would look like that, right? Now this is not necessarily symmetric then, because for example, this is not always symmetric. So while this is more general, it's not necessarily going to work out for you. So for example, let me just give you a specific, maybe I could add to that. Okay, is it okay if I add a column over here? So let's say that let's choose non-zero. So you know how over here I chose complex numbers that were units, right? What happens if I just choose complex numbers? So for example, real numbers under multiplication are in here, okay? So let's say that I use the number 2 in this direction. What's the inverse of 2 as a multiplicatively? What do you have to multiply 2 by to get 1? 1/2, right? So do you agree that I'm going to have a half here? Okay, so what does the matrix look like? Now it's 0, 2, a half, 0. See that? So this is not symmetric. Okay, and as soon as your matrix is not symmetric, things get extraordinarily complicated very quickly. Okay, as soon as you don't have symmetric, you can't guarantee you have real eigenvalues anymore, which is bad because what the goal is to relate the eigenvalues to parameters from the original graph. The whole point is you want to create a nice enough matrix so that these eigenvalues are nice. Okay, so what you have to do if you're trying to go to a more general group is you have to come up with a clever group so that the matrices end up being nice enough. Okay, I'm not saying you can't do anything with this system over here. Some things actually have been done for these types of gain graphs, but it's not nearly as nice as it's going to be for the complex unit example. Okay, so one group you could actually consider that's somewhat complicated. By somewhat, I mean fairly complicated, is, well, you know what, I'm not even going to spend time writing it out, but you can actually generalize the complex number system to the quaternions, which is sort of like a 4-dimensional version. You know how the complex numbers are sort of like a 2-dimensional version of the real numbers? There's really not a really good three-dimensional analog, but there is a good 4-dimensional analog, which is these quaternions. And instead of just having an I, you actually have a J and a K as well, and they satisfy a nice relationship with each other. But once you go up to the quaternions, you don't even have commutativity anymore when you multiply things. So your matrices still end up being sort of analogs, but you sacrifice the commutativity, so it gets more complicated. Okay, so that's actually something I've been working on for the past few years. So in my thesis, when I was working on my PhD, I actually worked on this family, these complex units, and these matrices. Okay, and trying to see how much of the theory from graphs and sign graphs generalized to this structure. Okay, so it's not too bad to define this stuff, right? To at least tell you what it looks like, okay? But the nice thing, why do I care about this family? Well, this family actually generalizes both sign graphs and graphs simultaneously, because if you are allowed to pick complex units, I can certainly pick +1 and -1. So this is a much more general family. See that? And then that's why I started looking at other groups. Okay, are there other clever groups that you could pick so the matrices are manageable? And one possibility is these complex units. So you know how quaternion units. So the complex units create this circle in the complex plane. Okay, so here's C star. The complex units are right here. Okay, so you can pick anything on that circle. So +1 is there, I is there, -1 is there, and -I is there. But also anything of the form, if I put a theta there, this is e to the I theta. So anything of that form is a complex unit. Again, complex units are complex numbers such that their absolute value is 1. So geometrically, there'll be something on that circle. I can't really draw the quaternions for you because it's 4-dimensional, but you can kind of think of it as the quaternion units as an analog of this. You would actually end up with a sphere in 4-dimensional space. You can kind of think of it like that. Like, you know how if you go up to 3 dimensions, you have a unit sphere, right? So like in R3, you know how you could have a sphere where everything is unit distance away from the origin? You guys kind of see this, right? You can generalize that to any dimensions in Euclidean space, Rn, and then I could just say, okay, give me all the vectors that are distance 1 away from the origin. So you can kind of think of the same thing that's happening in the quaternions. It's just more complicated. So you know how C is A plus BI, where A and B are reals, and I squared happens to be -1, right? Well, the quaternions you actually have to go up one more dimension, but you end up getting a plus bi plus cj plus d times k, and a, b, c, and d are real, and I squared is equal to -1, but so is j squared and k squared, and also I times j times k. Okay. So there's an analog out there of complex numbers, and just like here, how I could actually represent the units in this nice polar form, there actually is sort of a polar form for representing the units. So if I just write it like this, it would be this, it would be the things in h such that the absolute value of h is 1. So the definitions actually carry over very well. The definition of how far it is from the origin is exactly the same. You just use like Pythagorean theorem, generalized version of that. It's just I can't give you a nice visual for it because it's in 4-dimensional space. But in your mind, you could kind of think of it like this. It's just generalized beyond that, so you're not going to really be able to come up with a good picture, but your brain can do a good enough approximation of the picture. Okay. Okay. So is this somewhat? Do you guys kind of understand why you might be interested in these more generalized structures? That if the matrices and if you can generalize things up here, you actually get the previous cases as specialized situations. So whatever you can prove over here will translate to something for these specialized cases. Okay. Well, some things generalize. Yeah, I'll show you in a little bit. Like, for example, do you remember the upper bound where if you sign everything -1, the Laplacian eigenvalue is maximized? That actually is still true here. And it's actually still true in the quaternion case too, but that one is a lot more complicated. Okay, so these are some graphic structures. Okay, so if you find this interesting, there's not, this is kind of an active area of research right now. Not just me, like there's other people that are looking at this. Okay, even the sign graphs, like not everything is known there. So there's a lot more known about graphs, but the sign graphs and these other cases, not as much known. Okay, let me show you another family of objects you could look at and try to generalize. Okay, so another family is what are called hypergraphs. Okay, so these are all graphic structures. Okay, you also have hypergraphic structures. Okay, so for example, a hypergraph okay, so this is a hypergraph. Okay. Now, what's going on here? Well, this shaded triangle and this shaded square here, what those are is you actually treat those as one edge. So an edge is allowed to have more than just 2 endpoints to it. You can have an edge. So this hypergraph has 3 edges. So E1, E2, and E3. So edges can have many endpoints. Okay. In other words, you can think of an edge as a set of vertices, and you're not just limited to sets of size 2. In fact, you can even have an edge with just one endpoint, and it would look kind of like this. So it could be a singleton set. So it could just be that edge. So not even a loop, right? A loop you could think of it as having 2 individual endpoints. Okay. So it's much more general. You see, graphs are just hypergraphs where all the edges have size 2. Okay. See that? Like this edge has size 3. How many vertices are in that set? This is kind of your normal edge, right? And here's an edge of size 4, and here's an edge of size 1. Okay. i.e. sizes, like you can have a size other than 2, right? Is that okay?
So you wouldn't really think of those as cycles?
Well, yeah, a cycle you would try to kind of generalize in the graphic sense. I should be able to go from a vertex back to itself by a sequence of edges and vertices. And currently, yeah, I guess you could say that that's like an internal cycle. Is that kind of what you're saying?
So I'm just thinking, like, can you have like that, and then also a different edge just between one of those two vertices?
Yeah, you could have another edge here for sure. That's totally fine.
But like two vertices in the same, like E1, if you have two vertices connected to E1, like instead of having a edge of size 3, just have like an edge of size 2 as well.
Oh, for sure. Yeah, yeah. I could have like another edge like that. Is that what you mean?
But connected to another vertex that's also.
Oh yeah, that's fine. Yeah, that's fine too.
Yeah.
Yeah. That would be generalizing like parallel edges. Yeah, yeah, or multi edges. Yeah, you could even have. You could have. I mean, it could even be other than size 2. You could have another triangle here. You see, so it's much more general. Yeah. So this would be like E5, E6. Much more general, right? Okay. Now, if you try to do spectral graph theory over hypergraphs, there's sort of been different methods that people have done that over the years. But that's still a very active area of research. People are trying to figure out what is the best version of spectral graph theory for hypergraphs. So one avenue that you could go is just using matrices, and another avenue that people have gone down is using tensors, like sort of multi-dimensional arrays. Okay, so one thing I was looking at with Lucas Rusnick, who we both had the same advisor, he was trying to generalize hypergraphs so you could have like a signed graph version. Okay, and sort of the version that you can end up with, I'll sort of draw this for you. I'll just draw a simple example. Okay, what you do is, let's say that this edge has size 4. So this square, you just have 2 edges. Okay, what you do is every vertex and edge meets. Okay, this edge of size 4 has 4 vertices, right? And there's a certain number of times that the edge meets the vertex. And I'm just highlighting that in red. That's called a vertex edge incidence, where they actually meet one another. And what you do is you label that as either a +1 or a -1. Okay, so you don't label the edge, you label where the vertices meet the edges. Okay, so this is like a +1, let's say +1, -1, -1, and then here's another vertex edge incidence. Here's another one, +1, -1. So that's one way to draw it. Or what you could do is you could use arrows instead. It's a lot nicer looking if you use arrows. Okay, so here's my picture. So +1, you'll say that you have an arrow going in. Okay, and -1, you'll have an arrow going out of the vertex. Okay, so +1, -1. We okay with that? So this right here is what's called an oriented hypergraph. And this is supposed to be a generalization of sign graphs. But actually, if you stare at it long enough, you'll realize, well, it's actually sort of a generalized version of these bidirected graphs. You see that? Where you have two directions on each edge. And the reason for that is there's an actual connection between these. If you give me a bidirected graph, there's a natural way to produce a sign graph. And if I have a sign graph, there's several ways to associate these bidirections to them. So there's a nice connection there. Okay. So the only thing that's different from the ordinary graph situation is a single edge does not have just a sign associated to it. Okay. Instead, what you have, I'm not going to draw it in here, is you give me 2 vertices that are connected via some edge. What I can do is I can figure out the sign of the adjacency that they form. So you see that these 2 vertices are connected via this square edge here. Well, I have these 2 directions, and so that gives me an adjacency. Okay, so looking at this one, since it's only size 2, it's not too bad. Do you see that these directions agree with each other? So we would actually say that that adjacency is positive. So it's a positive adjacency because there's no disagreement, okay? But this one, if I tried to go from this vertex to this vertex or vice versa, do you see that they're sort of in conflict with each other? Like I'm flowing out and then I have to flow against the current. So we would say that this adjacency is a -1, okay? Between these two, that's a plus. You see that? And this is a plus, and this is a plus. Okay, and then this is a minus. So actually what you have is for every edge of size, say 4, you actually have inside of it, you kind of have a complete, you see that you have a K4 where you're going to assign a sign to each of those. Okay, but it would be ridiculously complicated to try to draw that. So just to simplify it as much as possible, you just sort of label, you give each end a sign like this. Okay, that somewhat makes sense. Now, if you take that version of the definition that I just described, you actually can generalize sign graph theory. So you have nice matrices and things like that. For example, one of the first things I showed you could do with the adjacency matrix is do walk counting. Do you remember that? Well, with sign graphs, you actually still get walk counting, but walks have signs to them. So it's sort of like a signed walking theorem, okay? And right now, chemists and biologists use these hypergraphs to actually to give you a visualization of how if you have a sequence of reactions, you can create a hypergraph associated to it. And they're interested in when you actually do have cycles in that structure. And it turns out that that's really hard to actually find them. But we were kind of hoping maybe you could use the eigenvalues to give you some nice approximation. Okay. Any questions, at least the general structure? I'm just trying to give you guys a general idea, and then maybe I'll show you some results. Does that sound like a better approach rather than just doing a bunch of slides? And maybe you can just ask me some questions along the way. Okay, now Lucas was working on this, and so I worked on the generalized results of, about matrices with him. And he already had some, but then we worked together and we generalized that. He was also interested in some other structural things specific to this. So he was trying to generalize some things that were known about hypergraphs and sign graphs that had nothing to do with matrices. But because I really liked the linear algebra, I really wanted to do a bunch of that stuff. So we worked on that together. And then what I did also at the same time was when I was looking at this complex stuff, I was thinking, oh, well, there's got to be a way to generalize this stuff to hypergraphs as well. And I came up with a version where you could do it over any group. Okay, so actually the full gain graph generalization. Okay, so that's what I kind of worked on for a little while. So this would be, I called them G-oriented hypergraphs. Okay, and the version that I came up with is it's pretty natural. It's just that you had the definition. Coming up with the definitions is always the hardest part. You come up with the definitions so that the proofs are as simple as possible. Okay, so the hardest part is sometimes coming up with the correct definitions. Okay, and so you're not going to really be able to just give like a direction like this, but what you can do is you can label each point where the edge meets a vertex. You can label it with a group element. So let's just call it like G1, G2, G3, G4, G5, G6, where these GIs are elements of your group, okay? And just like I mentioned that there is a sign of an adjacency, there's actually a group element that you would associate to the adjacency. And the way to compute that is a little bit more complicated, but it's related, okay? So maybe I'll draw it in for you in one instance here. So you kind of have an adjacency from this vertex to this vertex. And the way you compute it is you take the negative of the product of these ends. So you see how I have +1 and -1 there? It would be negative +1 times -1. And what is that? That's +1, right? But you remember how I gave you an intuition without saying what the formula was? I just said if they agree with each other, it's +1. Okay. So you just take the negative of the product. Down here, it gets more complicated. So you would have an adjacency here, and not every group has a negative. So what you do is you actually have a special element that we're just going to call S, but you can think of that as like a negative. And then you take G5. It's actually going to be G6 times G5 inverse. To make your life as simple as possible, you could just pretend it's just +1, and then that's how you compute this gain. And then the gain in this direction will be S G5 G6 inverse. Okay, and if you want, you could just think of S as being +1. But S is a special element that behaves like -1. Okay, it actually is a commuting. It has to be able to commute with everything in the group, but the group itself does not need to be commutative. So it's quite general. So for example, I looked at, so this is the definition I came up with. And then what I did was I specifically looked at the complex unit case. So there, everything is commutative anyway. You don't really have to worry about it. And your S's there are either +1 or -1. All right. So what that means is if you looked at that system and you said, okay, well, now let's restrict it. So whatever theory I prove, let's say all edges have size 2, then it would bring you down into this realm here. It would bring you down to the graphic realm. Okay. Yeah, I'm not saying that that's easy to understand. This actually hasn't even been published yet. This general, I mean, it's in my thesis, so it's like published in the sense that it's available. But I wrote up something this past fall on the complex case, and then I was hoping to do some more stuff before publishing the general case.
How long did that take you to figure it out?
Okay, so it was, yeah, that's a good question. So I was working on this problem for a year or two, a lot of this stuff, right? And simultaneously, I was looking at this and this, and when I came, the definition that came up here actually sort of naturally came up with another problem I was looking at here. Do you remember I showed you guys what line graphs were? So I tried to come up with a definition for line graphs of these things, and by doing that definition, this definition sort of naturally came up. So I would say it took about a year. And the funny thing is I had a definition, right? And then I would prove stuff, and then you would say, okay, this doesn't work, but then this thing does work, this other thing. And then you would go back to the drawing board and you would come up with a definition, and it would fix one thing, but not the other. So it was like you kept fixing one thing, but then not the other. And then you had to come up with this definition that had sort of, it's still general, but has enough flexibility that everything you wanted, at least what I wanted. Maybe there's some other things that don't work still, but that version of the definition seems to work the best for what I was trying to do.
I'm guessing S has to have some sort of property.
So S, the only properties S has to have, so S is still in the group, right? But the properties are S has got to be in the center of the group, which means it commutes. It commutes with everything. All that means is I'm free to move S anywhere that I want, even if the group itself is not commutative. But if we're talking about complex units, you can move these things anywhere you want anyway. So if the group is commutative already, it doesn't really matter. And then the other property is it has to be that the square is the identity of the group. So for example, -1 squared is +1, and +1 squared is +1. So if you're talking about complex numbers, those are the only two that will satisfy all this. Okay. But the reason I had to do that is because if you just say, okay, let's try to do all of this over Z2, right? Well, there's no -1 there. There's something equivalent to -1, which is +1, right? But or let's say you're in Z3 or complex units where you just have the third roots of unity, you have a +1 in there and you have these other two roots, but you don't have a -1 in there. So sometimes you have a -1 and sometimes you don't have a -1. And so that was the thing we were trying to wrap our head around, is we were trying to figure out what the heck to do, because that negative there just naturally comes up. So how to fix it was the problem. Yeah. Sorry?
Is it normal? Or do you not know that? Like a normal root? Or,
Like a subgroup?
yeah.
I mean, you could look at gains, you could look at labels that come from a subgroup. I mean, we weren't doing anything where you naturally came up with like factor groups and stuff. So the normal thing never was really an issue. Maybe there's something out there that you could do where you have a gain graph and then another gain graph that have gains that come from the subgroup, and maybe there's something interesting there, but yeah, we didn't do anything. Okay. Does this, does some of these structures seem somewhat interesting? There's a lot of unsolved things still. Okay, so like if you just are interested in the matrices of this, or maybe the sign graph, or these general things, there's still a bunch unknown here. And there's still, well, there's practically everything is unknown for the general structure, but the only thing that's been published that's about the more general situation is if you take G to be complex unit. And that actually isn't even published. We just submitted it. It's on the archive. You can read it. I did that work with Rafaela Mulas. And yeah. And this oriented stuff, yeah. There's a bunch of random little things. I could show you guys if you're interested. Now that that complex paper is done, there are some approachable questions I could have you guys do, and I could show you some things that I had other students work on along the way. I had one student work on me with the quaternion case. That was last year. Nolan Coble. I don't know if any of you. He worked. That was part of his honors thesis. Was working on one particular section of that, and then Luke Duttweiler. Did any of you were any of you around? So he was a graduate student that graduated a couple years ago. Okay, so maybe. So I had him look at the oriented hypergraph case and just calculating some eigenvalues of specific families, because while I was able to give you general results, we actually didn't have that many families we knew the exact eigenvalues for. So I had him work on that. And then another student who's now graduated, Will Kitatuni, I think is his last name. He worked on the oriented hypergraph situation where we came up with a bound, a lower bound for the Laplacian eigenvalues. Okay. So one open question that I'm thinking about right now is in Luke's work, I gave him a family of oriented hypergraphs. For example, the family is, maybe I can just show you. We still have a little bit of time, right? Or did I promise you I'd let you go early again? I can't remember how many promises I've made. All right, so I might come back to this. This is just some slides to go over what it looks like with the gain graph situation. So if you're interested in the gain graph side, I could come back and show you this. And then here's sort of the hypergraph. I had some slides where I was just explaining how you get to these things. So you start with a hypergraph and you add these labels, okay? And that's how you get an oriented hypergraph. So you just start with a hypergraph. Again, remember, a hypergraph is the shaded, this pentagon and a triangle. Just think of it as an edge. It just is one where you're allowed to have more than two vertices in an edge, okay? So that's how it's generalized. And you label all the incidences. So wherever a vertex meets an edge, you label that as a +1 or -1, but that picture looks awful, right? So what you do instead is you use arrows because the picture looks a lot nicer. And then the red thing here is this adjacency business that I was talking about. So the formula looks complicated, but it's really not as bad as it actually is. It just looks complicated because you have three things going on. You have two vertices, right? You have two vertices and you have one edge. And the reason you have to write all that is because your edge may have many vertices. you have to say, okay, I'm connecting V2 to V3 via this particular edge. Okay, so what's the sign of that adjacency? You just take the negative of the product of the two labels on the endpoints. So see, it'll be negative, and this one is a +1 because it goes into the vertex, and this is a +1 because it goes into the vertex. So that adjacency is negative, but the intuitive way to just think about it is, do you see that these arrows disagree with each other, right? When you're flowing from one vertex to the other. So that's why we give it a negative adjacency. Yeah.
Is there like a way to determine like how you sign the graph, I guess?
You do have an adjacency going the other way, but for sign, for the formula will still be negative the product, and you see it'll give you a -1 this way.
But when you like made the sign graph with the -1 and the 1, or like just adding those in?
Oh, that was just arbitrary.
That's just
Yeah, you can choose to do this with that. So that step where you add that, see, that's the flexibility. You get to do whatever you want.
Oh, cool.
So the nice thing about that is, well, yeah, you have all that flexibility. Do whatever you want. Okay. Now, if you have an application, though, you might be specifically limited to how you're doing this. But the next step should illustrate why this is so useful. So if you go to the adjacency matrix, well, it's going to obviously be a little more complicated, but it's actually the same definition that it was for graphs and sign graphs. All you do is where these two vertices are connected, you just figure out what the sign of the adjacency is, and you put that in the matrix. And it's going to be in two spots because you either can go from vertex A to vertex B or vice versa. So the matrix will still be symmetric. But the really, and you have a Laplacian, so take all the degrees. The degree is still the same, like vertex, however many edges a vertex is connected to is the degree. But actually, one of the cooler matrices in this context is actually, I didn't even write it in. Okay, that's unfortunate. Maybe it's later. Is you guys remember the incidence matrix? Okay. So in this situation, the hypergraph situation, you're going to have each column is an edge, right? But in hypergraphs, you can have edges as connected as many vertices as you want. So you could actually have a column of all ones if you wanted, meaning that the edge is connected to all the vertices, or it could be just 1, or even 0. You can have an edge that's connected to nothing, but it's kind of a boring edge. What that means is there's actually a if you give me a matrix that has zeros, ones, and -1s, make any matrix you want, you can associate that to an oriented hypergraph. So there's a correspondence between +1, -1, 0 matrices in general to this hypergraphic structure. So that's not the case with just graphs, right? If I tell you that this is the incidence matrix of a graph, each column only has 2 non-zero entries. So you don't have as much flexibility there, right? So what I'm telling you is if you ever come up with a matrix that has 1s, -1s, and 0s, you can create this combinatorial structure, and perhaps that tells you something useful. Okay. So just like before, you would try to, this is what you're trying to do. Take a hypergraph, associate a matrix, look at the eigenvalues. What do the eigenvalues tell you about the matrix or and the graph? In this case, a hypergraph. And what does the hypergraph tell you about the eigenvalues? Okay, so you do have, I'm not going to go, you do have switching, and it's actually exactly the same. You know that lights out game where you can swap the signs of edges associated to a vertex? You can do the same thing for the hypergraph case. It's just you only swap what the vertex, the incidence is specifically that it's connected to. Okay, and that doesn't change the eigenvalues. And there's bounds. Let me just skip this. So there's bounds, blah, blah, blah. That's some stuff that I was working on. This is the thing that I was working on with, that I gave this problem to Luke, okay? So the question is, okay, that looks complicated, but what I'm just trying to do there is generalize the idea of a cycle into the hypergraph world. And my question is, could you calculate the eigenvalues of such a thing? Okay. Or even, and this is much more general because you could have edges. So how would you generalize a cycle to hypergraph world? Well, the first picture on the left here is every edge has the same size. They all have size K, okay? The little one here, let me just take away that. Okay, so the K is how big each edge is, okay? The one there is consecutive edges share that many vertices. So you see they share one vertex. And the M there is how many total edges you have. So that's how you would generalize. Let me just go back to a picture world where we're still awake, right? Okay, everyone agree that this is a cycle, right? So here's C4. Okay, if you try to generalize that to a hypergraph, there's too much flexibility there, right? Because I could have a triangle, okay? And then I could have, I don't know, another triangle. I could have a square. And then I could have pentagon, right? So this is still something you might consider a cycle, but what's stopping you from doing this? What's stopping you from going, okay, let's say that I have a square, and then another square, and then another square, and then another square. So see, that's still sort of a cyclic structure. It's just really complicated. So what I'm trying to do is simplify it as much as possible so you could attack that problem first. So one way that you could do that is, okay, here all the edges have size 2 and they share one common vertex. So the simplest way you could maybe generalize that is, let's go up to size 3. So all edges have size 3 and consecutive edges only share one vertex. You see that? So that right there would be, okay, it's still a C4, but I'm going to add these other parameters up top to tell you how big the edges are. So that would be a 3 and a 1. See that? So the 3 there is how big each edge is. And the 1 there is how many vertices do consecutive ones carry. So I asked if Luke we could calculate the eigenvalues for this. And then once we do that one, then we could try to do the more general situations, like maybe they share 2 vertices and so on. Okay, so now going back to this picture, okay, maybe the next picture will make more sense now. Do you guys see that? So for example, C6, 6, 3, the 6 on the bottom is just like it was with graphs. You have 6 total edges. The 6 up top is how big each edge is. Do you see that each edge has 6 vertices within it? And the 3 there is each of them has 3 consecutive. They share 3 vertices consecutively. You see that? Like this edge and the next edge share 3 vertices. And then you also have to simplify it even further. And I'm going to make it so all of the incidences are all labeled +1. Okay, everything there is labeled +1. It's actually an unsolved problem, I think, if you try to do it haphazardly here, because it gets complicated extremely fast. Okay, so here's actually some results. So if if the number of vertices that consecutive edges share. So for example, this picture here, I have 6 edges. They're all size 6 and they share 1 vertex. See that? As long as the number of vertices that consecutive edges share is less than or equal to half their size. So for example, this is size 6 and 1 is less than or equal to half their size, which is 3. It turns out that the Laplacian eigenvalues follow this formula, which is the size of the edge plus 2 times the number of shared vertices times the cosine of 2 pi j over m, where m is how many edges and j just ranges between 0 and m minus 1. Okay, so there are your 3 parameters. You have the size of the edge, how many vertices the connected ones share, and how many total edges you have. This is a really simple formula, right? It's kind of pretty. All right. If you find that interesting, I can show you how you could attempt to generalize this type of problem. Okay. But I think we're out of time. So more on that on Wednesday. Is some of this interesting? If not, I'm not going to be offended, but I'm just trying to get to the point where maybe you could see something you could attempt to solve. And then I'll probably also eventually show you how this is generalized to chemistry, actually. So there's some really cool chemistry applications. So when I was solving this problem, that's actually how I met Rafaela, because she solved it first. And I was like, oh, you solved that. That's really cool. But then we ended up doing the complex case together. So it's good to be scooped sometimes. Yeah, and then I could also show you some applications to Hadamard matrices, which those have a lot of applications. So yeah, okay. I will see you guys on Wednesday. Show you some more stuff. At bare minimum, I'm just trying to get to the point where you guys can see an unsolved problem